So we will discuss fourth assignment today, and there is a 18 question. So let's discuss first question. Sorry. Upon applying forward bias to a PN junction, in this assignment we will discuss PN junction totally. Okay. So these are four options. Upon applying forward bias on or to a PN junction, first option, the whole diffusion current from P side to N side increase, the whole drift current from P side to N side increase, the electron diffusion current from N side to P side increase, the electron drift current from N side to P side increase. If you know, please tell me the answer. You can text me in chat box your answer. Yes, please. So let's discuss. Do you know PN junction? Let's say we have P type, we have N type semiconductor. This is depletion region. So upon applying forward bias to a PN junction, P terminal is connected to positive and negative terminal connect to N side. So this is called forward bias. Okay. So upon applying forward bias, what do you know how N side and P side minority and majority charge carrier? In P type, holes are majority. In N type semiconductor, electron are majority charge carrier. So what when we bring together these two, so first they form depletion region between these contact, okay, and due to concentration gradient, hole this side is higher as compared to electron, so hole diffuse from P side to N side initially, and electron from N side to P side initially. Okay, so this is called diffusion. And this current is known as diffusion current due to the concentration gradient.
Sir, diffusion current and drift current. What is the difference?
Okay, let me tell you. Yes, so diffusion means term is clear. Diffuse, something is diffuse. When diffuse due to the concentration gradient. Okay, let's say number of holes is measured, and 2 3 are there. So all are diffused due to the concentration gradient. Concentration gradient. Okay, so this is if electron and holes are moved, they generate current, and this current known as what? Diffusion current. But in the presence of electric field, let's say here is majority is hole and minority is electron. When we, let's say, bring together these depletion region are formed, so electron and hole are now when the reach the equilibrium, electron or holes are not more diffuse, but we apply the current. So what will happen? Positive or ripple, they cross this side to this side hole again now, and electron also feel negative and negative. So due to electric field, what? Due to electric field, applied field, if electron and holes are moved, this current known as drift. Clear?
Yes, sir. Thank you, sir.
If diffusion when will happen? If the concentration gradient is there, known as diffusion. But if the electric field is there and charge carrier move due to the electric field, this current is known as drift current.
Yes,
Okay,
sir.
so now you can check your answer. This is right or wrong. Please think about this. One thing. Yes, this is right. What it is? The hole diffuse from P side to N side, as you can see in this picture, and C, the electron diffuse from N side to P side. Okay, so we have already discussed in this picture. I think this is clear to you. Clear to all of you? If question asks like that,
Yes.
let's say this is forward, let's say reverse. Then what will happen? Think about this. Okay, if you this is clear, then you will also can think about like that. What will happen? Do you know Coulombic force? Electron are feel
Equals to
repulsion force, but electron and holes they are attract. So this concept will apply here, nothing else. Okay, sorry.
Okay,
Next
sure.
question: what happened to the width of depletion region upon heavily doped the N side in a diode? These are the four options. The depletion region width decrease on P side, depletion region width increase on P side, increase or decrease, depletion region width decrease or increase, P side or N side. These are the options. So what is question? What happened to the width of the depletion region heavily doped N side diode? So do you know what is N type semiconductor and P type? This is conduction band, this is valence band. Somewhere mid is intrinsic, let's say. This is for intrinsic semiconductor, Fermi level. But for N-type, near to the conduction band. This is for N-type semiconductor. Why this is closer to the conduction band? Fermi level. Charge carrier, N-type charge carrier in semiconductor is more. You know, electronic energy increase this side and hole is the increase this side. Okay, so N side doping is small. Then what will happen to the depletion region? Let's say we have depletion region P side and N side in normal condition. Case first. Case second. If N is heavily doped, N plus plus, then please think what will happen. Sorry. So you can see answer. What is the answer? Depletion region width increase on N side. That much. Something like that. Why this is happening? Can you imagine why this? Why? What is the reason? How can you correlate? Let me understand. Let me give to you hint. Okay. Let's say we have p-type, we have n-type. In p-type, number of souls is greater than, and in n-type, electron is small. When we bring together, they form depletion region. Yes, yes or no?
Yes, sir.
So how? What will happen at the depletion region? Which charges are there? If hole is diffuse here to here and some like that electron is diffuse here to here. So which charges are there? If electron is less, this is electrically neutral initially, but electron is goes out plus charge will be there. Yes or no? And similarly, negative charge from p type. This is clear to you, all of you? Yes or no?
Sorry, I don't understand, sir.
Oh,
Sorry,
yeah.
I think positive and negative attracts. How it from depletion layer?
Initially, let's say number of holes is higher, electron is less, some electron maybe, which is are bounded. And you can see we have silicon. This is intrinsic. When n-type and when p-type, if we three three valencies and five valencies are sit to here, they form n and p-type. So according to electron and holes are there. This is I think too clear to you. Okay, so
Okay,
that's
sir.
why electron and holes are there to n side and p side. But now we make, let's say, p-n junction. P and n come together, and what will happen? If the concentration gradient is there, initially hole, let's say first hole is diffuse, 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 and electron also. So diffuse is leave behind negative charge on the this atom, one atom, let's say two nucleus. We have nucleus and some electron is revolving around. We know if one electron is out, removed from here, this is positively charged. Yes, if receive electron negatively charged. So same like that, if electron is donate to p side, this is positive. Yes, and this is receive here. Yes, this is will be negative. So that's why this code is acceptor, this is donor. So yeah, these charges are immobile. Why? This is to the atom, let's say plus 3 vacancy, let's say may apply. sorry, this will be 5 valency. So this is donate and take plus charge, a pair plus charge, because if the electron is donate. So this charge is on atom, cannot move. Okay, this is immobile charges. What it is? Immobile charges. Okay, so they cannot move and attach to the atom. Okay, these are not free to move, not free charge carriers. Okay, so initially they diffuse from some region up to some region. Then what will happen? Why not cannot go more? Because electric, due to the potential gradient, these are positive, these are negative, the electricity, yes or no? Positive, if potential difference is there, then always is electric field, and electric field oppose the electric field direction this side. Yes, this is the electric field direction. Let me change. This is, yes or no? So if hole is diffuse, they feel electric field repulsion, and electron also has electric field, so cannot. Similarly, they repel back again to the respectively type of semiconductor due to the depletion electric field. Yes, clear? In this depletion region, so finally let's say this is negative, 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 and this is positive, positive, and positive. This is depletion region, initially P and N. But if we doped heavily, what will happen? If number of electron is higher this side, let's say before is 50 and 50 whole, but now 70. This is assuming, I am assuming nothing, and 50. So concentration gradient is high as compared to this. So more electron can also diffuse. Yes or no? Because electron also feel repulsion force. So they can also overcome this electric field. Yes. Heavily doped means number of electron is more. Then what will happen? More concentration gradient is there. So more number of electron all can come from N side to P side. So that's why depletion region width, sorry, decrease or increase. Um, Here is the decrease. 1 minute. let's say initially 70 electron and 50 volt. So now, yeah, if number of electron is more, they feel repulsion force more, so they can push these this boundary. They apply also the force. Yes. So due to this, depletion width also decreases. Let me explain in deeply later. When we apply positive biasing, what depletion width increase or decrease? What will happen? Decrease.
Decreased conduction is easily electrons and positives are move rapidly.
Yeah. So
Like
in forward bias, depletion width is decrease, but in reverse bias, depletion width are increase. That's a negative connected. This is positively connected. This is N side is negatively connected. This is P. This is N. In this case, increase. So same way like this is negative biasing. If electron is higher, means negative charge is higher to that side. Same phenomena we can assume here. Negative charge connect to N side. This is called forward biasing, and forward biasing depletion width is decrease. Okay. So same phenomena we can think. Okay.
okay, sir.
Okay. Let's move to next question. For an unbiased p-n junction, that the thermal equilibrium which of the following statement is true? Yeah, drift and diffusion. Now please check your answer. Unbiased p-n junction, not biased. These are not connected to anything. At thermal equilibrium also, which of the following statement is true? J total, J current, these are the N side diffusion current, drift and diffusion, drift equal and negative sign. At equilibrium, what will happen? Is there any current flow? At equilibrium, thermal equilibrium also unbiased. No current, there is no current flow inside the material, also in the PN junction. Okay, so concept, there is should be no current inside. So option A, C and D. Drift and diffusion. Due to the concentration gradient, there is diffusion, and drift will due to the electric field. This is due to the electric field, and this is concentration gradient. From n side, let me electron is diffuse n side to p side, and drift what will, if there is electric field, electron also come from this type to this side due to the before the equilibrium. But when the equilibrium is achieved, these two current opposite current arcs should be equal. So diffusion and plus drift should be 0 at equilibrium. Okay, similar way for P, drift and diffusion. So option according to A and P also. And what is this? Diffusion N and diffusion P also should be equal. They confirm no more is diffused. Okay, so these are the option, right option. Let's move for next question. Consider the unbiased p-n junction diode in thermal equilibrium and under dark. Thermal equilibrium and under dark. There is no light. When forward bias voltage is applied, then what will happen to the Fermi level of n side? The Fermi level p side is this, intrinsic is EI. Forward bias is applied, P and N. This is forward biasing. This is before, and when forward bias is applied, what will happen to the Fermi level? We already discussed this type question, more heavily doped, and so this is question is like to similar. So answer A, Fermi level shift is higher, and also B to the intrinsic and also the p type. Okay, this is question like a previous one, more heavily doped. So let's move for next question. If you want to discuss something, you can ask anytime for regarding these question. Okay, which of the following is valid for p-n junction diode? in an unbiased dark condition. Please think and write your answer in chat box. Which of the following is valid for p-n junction diode unbiased dark condition? P and N. This is unbiased and dark condition. Only generation take place in the depletion region. Only recombination take place in the depletion region. Neither generation nor recombination in the depletion region. Both generation and recombination take place in the depletion region. Yes, please. If there is no light and no biasing, what will happen? And this is at equilibrium. So there is no generation or recombination will take place in the depletion region. Only on when if light is there, electron or holes they get excited energy, they can create electron hole pairs, generate again recombine when light is there. Okay, or some field is there. Somewhere if we get energy, they can break the bonds and generates the carrier, charge carrier. So this is clear. Can we move for next question?
Yes, sir.
Okay. So this is the next question. When a reverse bias is applied to a p-n junction diode, so which option is correct according to you? Reverse bias. Now P is connected to the negative terminal and P is applied potential. Voltage is V. This is called reverse bias. Reverse bias condition. So raise the potential barrier for the carrier transport. This is P type, this is N type. There is a depletion region, band bending. As we have discussed in previous question, this is Fermi level, but if biasing is applied, what will happen? Fermi level goes up and down. So due to reverse biasing, they raise potential barrier for the transport in reverse biasing, but in forward biasing, they will help. What is the barrier? Do you know? For electron is higher energy this side.
Sir, the second diagram, I don't understand, sir.
That one.
This, sir. Yes,
Okay.
sir. Second diagram.
So before, let's say we have n-type semiconductor and one another have p-type. So Fermi level is closer to this side, and this is Fermi level for n-type. This is Fermi level for p-type. Okay, this is conduction. This is valence. This is valence. This is clear to you. Before the p
Yes, sir.
biasing, particular n-type and p-type. What will happen? They make p-n junction diode. Only one Fermi level will be there if equilibrium is there. So this Fermi level is joined, and in the depletion region, band bending is due to the due to the electric field potential gradient. So this region is depletion region. Only one Fermi level is now made. Okay, so now let me electron to the point. Electron energy higher this side, and hole energy is due to the charge negative and positive. Higher electric energy this side. Okay, so think about now for electron, for hole. Let's say we have electron here. They can easily come to this side. Yes, if the hole is there and hole is there, electrons somewhere easily go from here to here. Yes or no?
Yes, sir.
Hmm. But in the applied condition forward and reverse bias, what will happen? Let's say, sorry, electron wants to come to here in drift. Let's say electron and hole pair there. Electron wants to come to due to the electric field. Field is light. come air to air and hole air to air in depletion region. But let's say this is without biasing. What will happen if biasing is applied? P is connect to positive terminal and N is connect to negative terminal. Okay, so due to positive terminal they shift more upside. Sorry, yes, and this is goes to downside. Mm, this picture will be messy. Okay, I will not. This is clear to you, I think.
Yes, sir.
But now is potential is applied. How barrier is formed? Let's say, let me tell you, nothing is one diagram. Let's say electron is here, wants to here, go to there. So electronic energy is higher this side. If barrier is too high, let's say that much, due to the any applied reverse or fiber, let's forget about the dicing. So feel this energy should require more energy to get here to here. Yes or no? This is first case, this is second case. In second case, this is barrier. Yes or no? For electron, that much.
Yes, sir.
So same way, if we applied biasing p type or n type, barrier goes down or barrier goes up. In forward biasing, barrier potential barrier is low in forward, and on the other hand, in reverse, potential barrier is high. Okay, according to the Fermi level shifting. So please think about this, how barrier will go up and low when we applied the biasing. Okay,
Okay, sir.
so let's move for next question. For a forward bias PN junction diode. Yeah, forward bias PN junction. Now you can answer. Depletion region width is decrease or increase. Built-in potential increase or decrease.
Depletion region width decreases.
Yes, decrease. And also the potential is decrease. Built-in potential also decrease.
Yes, sir.
Why? This is forward biasing, let's say. This charge carrier is negative, 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 positive, positive, positive. Sorry, negative, positive, and this is P and N. So potential, built-in potential. Here is the built-in potential. This is due to the electric field. But if a positive terminal, positive charge carrier, let's say feel negative charge carrier, so what will happen? overall potential will reduce. Yes or no? This is to the negative terminal and positive. So overall effect is delta V goes down. On the other hand, if we applied reverse biasing, let's say in another case, then what will happen? This is also positive and this is also
Yes.
positive. Goes up. Okay. So these in last question also, these potential barrier charge carrier feel high due to the goes up, and in this case there is no potential. Will this goes down, so charge carrier feel low barrier. Okay, let's move on next question. The electric field in the bulk region PN junction under bias is positive, negative, zero, or sinusoidal. Electric field in bulk, not in depletion region. Ask some area. There is electric field. I am asking here. Electric field will be there or not? If let's say we have P type, this is electrically neutral, so there is no field. The same way you can think. Also, the in bulk there is no electric field because there is no minus plus gradient like that. No gradient. They can randomly distribute and overall will be zero. There is something, but there in bulk there is no gradient. In bulk, only the depletion region gradient will there. Delta V. This is give us the electric field built-in potential. Okay, let's move on next question. Yeah, charge density in the depletion region on the p side or p junction. Charge density. P side. Charge density is, let's say, rho number of charge into charge, electronic charge, and number of carriers. For p type, answer B you can think. Initially is neutral, but they accept the electron. Yes. So number of accept, let's say charge carrier accept Na. These accept number of charge carrier is Na, and electronic charge is Q equal to minus E. So you can write also minus E into A, or represent charge is represented by Q. So both are correct. Okay. So this is just formula for N type. What what is the charge density? Number of charge carrier. This is donor and positive charge on the other end. Clear?
Yes,
Let's
sir.
move for next question. Sorry. Which of the following statement is correct regarding the p-n junction diode under dark condition? So this is we have already done. E is 0 in the bulk region, but in the depletion region there is electric field. Free charge carrier density within the depletion region is 0. And current in the bulk region is determined by the diffusion of minority carrier in the bulk. Okay, let's discuss on numerical. A silicon-based p-n junction diode maintained at room temperature under equilibrium condition has p side and inside the charge doping. The value of the built-in potential B. So let's see. Answer is B. This is the built-in potential formula. KT by Q ln acceptor and donor divided by intrinsic charge carrier concentration is whole square. So this is formula. You can apply this formula, and KT by Q is 26 electron volts. So electron is cancel out. This is will be in volt. So value of KT by at room temperature will be that much. So use this value here, and we have acceptor and donor put there. So these are the acceptor and donor, and this is intrinsic charge carrier whole square. So if you calculate 10 to the power 8 ln multiply by 0.02 26 millivolt, you will get 0.479 volt. Yeah, you can check. So built-in potential KT by Q ln acceptor and donor divided by intrinsic charge carrier concentration whole square. Okay, so let's go next question. Clear? This question is clear to all of you? Yes? You can apply this formula, simple.
Okay, sir.
Okay, let's move for next question. Which of the following is correct Einstein relationship for electron and non-degenerate and non-uniform doping semiconductor? In previous class, we have already discussed Einstein relationship. So this is always apply. You can apply non-degenerate or degenerate. So this is relationship. Diffusion probability KT by Q. Okay, for electron you can use N, for hole you can P, for doped or undoped. Next numerical. A homojunction diode is under forward bias condition with applied potential voltage 0.2 volt, 0.2 volt, sorry. Given doping concentration on both sides P and N is 10 to the power 15 centimeter cube. An intrinsic charge carrier 10 to the power 10 per meter cube per centimeter cube at room 300 Kelvin. So what is the junction potential to the diode? So let's discuss. We have to find first built-in potential. Sorry. So built-in potential KT by Q ln except donor by Ni whole square. This is the formula. So we have already know. So this is the for built-in potential. So this is we have already done like that question. So you can easily calculate that much. And 0.2 voltage is forward bias. So we know forward bias P and N. Built-in potential is goes down. So that's why is my built-in potential minus to the applied potential. Okay. So that's why is minus here. Okay. If question asked like that, reverse bias, then what will happen? This formula P junction VBI plus VA V for reverse. Okay. So this is the answer. Clear to you?
Yes, sir.
Okay, so let's move for next question. Similar. So here is the question. What is this question? Diffusion coefficient of electron and holes semiconductor these 50.2 and 20.5 centimeter square per second. Diffusion coefficient, okay, respectively. And the carrier lifetime for electron holes also these. What is the ratio diffusion length? So for diffusion and tau, sorry, tau, this is the formula. If n, then you can use n. So ratio, so you can divide by simple this for whole divide, then get like that, and these values are given: diffusion coefficient and lifetime charge carrier. So put these value here, multiply and calculate the square whole roots, then you will get the ratio 0.443. So sorry, Answer will be E. I will correct it. Answer is E, but some typing error is there. Clear? Any doubt?
No, sir.
Okay, so let's move on next question also. Consider P and N, P silicon, P type and N type having these are Fermi level, they are Fermi levels. Which of the following true for thermal equilibrium when both of them they are joined together? So please now answer this question. I am expecting to all of you. We have discussed in first or second slide when we make join together.
Option D.
Option D. There is negative. Fermi level is only one Fermi level will be there. Okay. So now please think.
Option C, sir.
Yeah. So y is minus, not this is minus here. If we apply here. Both Fermi level is at the same height.
Okay, sir. Okay, sir. I understand.
Okay, so option C is correct answer. Next question. So this is the formula that discussed. A silicon PN junction diode consists of p-type region containing 6 into 10 power 16 per centimeter acceptor and n-type. These are the donors. What is the total depth width of depletion region in micrometer? If the applied voltage is equal to the 0.4 volt, these are the given value permittivity and space permittivity. So this is the formula for depletion width equal to, this is ks to ks epsilon by q acceptor donor sum divided by acceptor dot multiplication and effective potential at the junction to the power half. So you can calculate first VBI KT by Q ln NMD upon NI square. So from where we have already calculated, so you can calculate by yourself. You will get this number, and we have also 0.4, so V effective in forward condition. This is depletion region. Okay, if the applied voltage equal to in forward condition, in forward connection. What will happen to the network? Sorry, there is network issue today. Yes, we are here. So now put these given values. Relative permittivity is given 11. So Ks is also Es, epsilon s. Please read as relative permittivity. So 2 multiply 11.8 and epsilon at 0.85 10 to the power minus 14 already given. Q we know, electronic charge 1.6 10 to the power minus 19 coulomb, and acceptor and donor values are given. Put these value and multiply, divide, sum, add, subtract all. If we calculate according to the formula, according to the given value, we will get 18.26 micrometer. Any doubt for this question?
No, sir.
Okay, so you have to remember this formula. So Ks is nothing. Yes, please read it. These are the different notation, nothing else. This is relative permittivity. So this is the which of the following represent the ideal diode equation for PN junction. So this is formula for PN junction diode. I equal to I naught e to the power QA by KT minus 1. And you know, for PN junction, current will like that. Yes, this is side forward, this is reverse. Okay, so this equation is explained this curve. This is voltage, this is current. And I naught is reverse saturation current here. This is value I naught. When reverse saturation is occur, current goes to suddenly increase too much. This is breakdown of PN junction diode in reverse condition. Okay, so this is last question for today lecture. Which of the following represent the long bias approximation for PN junction diode? These are the diffusion length of electron and hole respectively, and these are the Xn and Xp are the end of the equilibrium depletion region in the N and P side diode. long bias approximation for p-n junction diode. Yes, please. Any idea?
No, sir.
So let's say you have electron and hole pair, and this is, let's say, total length. Let's say electronic diffusion length. Electron can travel that much only. This is L, and after this length, they can remain recombine with hole. So if the electron is travel that length, charge carrier travel to the there respectively in the p or n type side or cross to p to n. This length is no, during the diffusion. Let's say diffuse air to air. This is known as diffusion length L. 4. Which of the following represent the long phase approximation for p-n junction diode? So now B option is correct, but what is this? Let's understand. Xn and Xp are the end of the equilibrium depletion region. So Xn is greater than should the p diffusion length of hole, and Xp also greater than for n. So length of p for long base, let's say this is Xn. So diffusion length for long base hole cannot diffuse from. Okay, I will tell you the formation of the depletion region. So what is this? Depletion length of n side is greater than to diffusion length of hole. So what is this meaning? Hole cannot move from L side P side to cannot cross to the depletion region of 2n side. Okay, and similar also electron also cannot travel that much length because depletion sorry diffusion length is less to the depletion region of p side or n side. So this is concept. Let's say this side is, let's say, hole wants to cross. This is n, this is p, and this is hole wants to cross n side to p side somehow, but depletion region is too high length. Sorry, yes, this is too high xn for hole, they cannot transform from n-type to p-type. Similar way, from p side to electron cannot. Xn is xp is too high for electron in the p region. Okay, so depletion length should be greater than for the charge carrier. They cannot cross from p side to minority charge carrier cannot cross to the depletion region. Band Fermi level is formed. Okay, this is for minority charge carrier. So thanks for your kind attention. Let me give one more explanation. Depletion region in real meaning in laboratory is different and theoretical is different. Let's say we have p-type base or n-type base in lab. In real laboratory, so if you want to diffuse n-type and their interface, they form depletion region. But concept wise, let's understand. Yes, this is p, this is n. Okay, and you know this is silicon, Si, and three valencies. Let's say these are from, sorry, 1 minute. One electron hole pair. So this is, let's say, p type plus 3 valency. One electron from silicon, one electron from air, same bond. So you know how to make p type or n type. Yes. This is, let's say, plus 5 valencies atom for n type. So one electron, let's say 2, 3, 4. One is remaining. Similarly, only 3 electron, 1, 2, 3 is make bond, but one electron is less here. So one hole will there in the bonding. So this type is N and P is formed, but so that's why there is more holes. Majority charge carrier. This is electrons inside. Clear?
Yes, sir.
Now let's combine these N and P. What will happen? there is a higher hole. Let's say 2 electron is only there. Minority. These are minority. These are majority. Similarly, the majority charge carrier, 1 or 2 hole are there. Minority charge carrier. So this side is hole is high, this side is electron is high entire. So what will happen if they come to in touch? Tell me first. Electron from this there and hole from it, they can recombine. Electron can come to this hole, this hole, this hole, sorry, this. Okay, and what will happen? They can recombine and leave the positive charge on the atom. Let's say this electron is goes to p side. So what will happen? Initially is atom is neutral, but to the whole atom they get positive or negative. Positive charge, similar way negative charge if one electron hole pair are recombined. Yes, so this side is negative, this side is positive. Clear?
Yes, sir.
This is clear. Now more electron wants to come this side. Yes, because there is hole. Yes, so
Yes,
that's
sir.
but due to the plus charge this side, let me take another color. Plus charge, plus voltage, and this side is negative voltage. Therefore, potential gradient delta V. Yes, and this is equivalent to the electric field. You know, due to the potential gradient, there is electric field from P side to N side. P side to N side. Yes,
Yes, sir.
so this electric field, this electron wants to this, let's say, wants to go this side due to the concentration gradient, but electric field is now there. Initially no electric field is there, but now is electric field. So this electric field, electron can, what is the motion of electric field inside the electric field? Let's say electric field this side, direction of electric field this side. So electron, motion of electron, this will be this side. Let's say this is force on the charge carrier. You know the formula, electric field equal to Q into E, but electron has negative charge, so direction, so this is force, direction of electric field for electron opposite to the force. Okay, so due to this negative signal, electron can move opposite to the electric field in the electric field. Okay, so this diffusion electron cannot go from to here because this is field, there is electric field, and this is field force, which was repulsion force. I am correct? Did you understand?
Yes, sir.
Yeah. So this
Thank
electron
you.
cannot cross if has no more energy to the electric field. So after some time, if some electron and holes recombine, they can form depletion region, electric field region, and this field is opposed to the further diffusion. Yes, and the equilibrium is reached. Electric field is equivalent to the diffusion field. There is no further movement of electron and holes, and this region is known as depletion region. That much.
Thank you, sir.
Okay. So thanks for your kind attention to all of you. If any question you can ask, otherwise we will meet next Monday. You can ask from in next class if you don't understand. Please think about these questions and this concept. PN junction is important in semiconductor physics. If you know PN junction very well, you can understand anything in semiconductor.
Okay, sir. Thank you, sir.
Okay, so bye bye. Thanks. We will meet on next Monday.
Okay.